Okay, we're looking at more complicated examples of when we're discussing about amount of energy needed, heat energy here in this case, to change temperatures of things. So let's take an example where we've got something like 200 mils of water, which is at 20 degrees Celsius at room temperature. And into that, we're going to add 50 grams of copper rivets or something that are at 100 degrees Celsius. And the question here is, what's the final? So the idea behind this is that we'll have copper rivets and we'll have a container of water, and we'll add in the copper rivets into the water. These are at different temperatures, and what will happen is the copper rivets will cool down because they're put into cooler water. The cool water will increase in temperature, and so we should end up with a settling temperature where they both settle at a particular temperature, the same temperature. So the question here is, what's the final temperature of the water or the copper rivets, right? Okay, so what's the final temperature? Right. So how do we start to approach this problem? Well, first of all, we need to think about where the heat energy is going. So where is the heat energy going in this case? Or I suppose, which is going to give off heat energy and which is going to gain heat energy? Well, the hottest thing here is going to give off its heat energy. It's going to give its heat energy. It's going to lose its heat energy to the water. So what's going to lose heat energy? Well, the copper. And what's going to gain heat energy? What's going to gain heat energy is the water. Now, if this amount of energy is lost, and we're going to assume in this problem that there's no heat energy lost to any of the surroundings, the desk or the air around it or anything like that, right? And that's a normal assumption in these questions. If we lose the heat energy here, it must be gained by this. So if we lose this, if the copper loses the heat energy, that amount of heat energy must be gained by the water to heat it up. The heat energy lost to cool down the copper must be the exact same as the amount of heat energy in joules gained by the water to heat it up. So that's going to be the basis of solving this problem. So in other words, the heat energy, the amount of heat energy lost by the copper is going to be the same as the amount of heat energy gained by the water. Okay. So what are we going to do? Well, we're going to substitute here for Q. We're going to do M C delta theta. It's going to be equal to, well, Q for water here as well is going to be M C delta theta. Now, this is a problem because here you could just go, well, M divides across by M, divide across by M, we get rid of M, divide across by C. These are different masses. This is the mass of the copper, so we need to identify that as the mass of the copper by putting a little C there, or subscript C. This is specific heat capacity of copper because we're talking about a copper substance, so specific heat capacity for copper. And then delta theta, we're going to talk about that in a second. I'm going to put a 1 beside that for now. Over here, this isn't the mass of the copper anymore. This is the mass of the water, so we're going to put a W there for water. And C here is the specific heat capacity of water because we're talking about water being the substance, and delta theta 2. Now let's look at these delta thetas for a second. Delta theta is the change in temperature. So the copper is going to start at 100 degrees Celsius, and it's going to come down to some temperature. Let's say we could go forward in time and we could figure out, we could see at the end of this experiment that the overall final temperature of this, this whole experiment was 45 degrees, right? So we start at 100 and the temperature for the copper rivets, and that drops down as far as 45 degrees. So what's the change in temperature there? Well, it's 55 degrees, right? The copper would have dropped from 100 to 45 degrees, which means the overall change in temperature would have been 55 degrees. How did we figure that out? Well, we said 100 minus 45. And that gave us 55 as our delta theta 1, right? But we don't know that that's going to be the final temperature. This was just, I was imagining if we could go forward in time and figure out that this was the answer to the question. We don't know the answer to the question. So instead, what we're going to do is we're going to say 100 minus x. We're going to call the final temperature x. And that's going to be our delta theta 1. Now, the reason that I have 1 here is because this change in temperature is going to be different. This is the water that we're talking about. So that's going to start at 20 degrees and go up to some temperature. And it's going to end on the same temperature, but the actual change could be different. In other words, if you take it that, let's say I was right here. Let's say this whole thing finishes at 45 degrees Celsius in the end. Well, in this case, the copper would have reduced in temperature by 55 degrees. But the water would have increased in temperature by 25 degrees, which is different. So there's a different change in temperature here. Let's see, what are we going to put in for delta theta 2? Imagine that I knew, again, let's imagine that we could zip forward in time and we could figure out that the final temperature was actually 45 degrees. Well then, what would my change in temperature be? Well, I would move from 20 degrees to 45 degrees, which would be 25 degrees. How would I have done that? I would have taken my 45 degrees, I would have subtracted my 20, and I would have gotten 25 degrees Celsius like that. But I don't know this value. That was just me imagining that I could know the value. Instead, what I'm going to say is I'm going to call this x, and I'm going to say, right, it's going to eventually hit a temperature of x, so x minus 20 then is going to be what I'm going to put in for delta theta 2 now. Okay, let's start filling in some of these values. Mass of the copper I have, it's 50 grams, but I need to have that in kilograms because we're going to keep everything in SI units for this calculation so that we get SI units out at the end. Mass of the copper is 50 grams, that's 0.05 kilograms. Specific heat capacity of copper is kind of a known value. It's 390 joules per kilogram per Kelvin. And then here we said for delta theta 1, we're going to put in 100 minus x. On this side of the equation, the mass of the water, it's 200 mils of water, and we know that the density of water is 1 gram per milliliter, 1 gram per centimeter cubed. So if we have 200 mils, it means that we have 200 grams, and 200 grams in kilograms is 0.2. Right, specific heat capacity of water, again, a known value, 4180 joules per kilogram per Kelvin. Sometimes it's given as 4,200, but we'll stick with this value for now. And delta theta 2, we said, would be x minus 20. Now what do we have? Well, we have one full equation like this. We've got one unknown, which is x. It appears on either side of the equation, but we can solve, it's still one unknown. And so we can solve for this. One equation with one unknown means that we can definitely solve for it. So how do we go about solving for it? Let's do the steps. We have to multiply this 0.05 into the 390. So 390 by 0.05, and that gives me a value of 19.5 multiplied by 100 minus x in a bracket. Over on this side, we have 0.2 multiplied by 4180, which is 836, and that's multiplied onto x minus 20, like that. Now we have to multiply into this bracket here. So how do we do this? If you remember from maths class, we have something sitting outside the bracket, so we have to multiply this part onto here once, and then we have to multiply the 19.5 onto the minus x second. So we'll do that now in a second. Let's see how to do that. Well, 19.5 by 100 first is easy enough to do. You just move the decimal point a couple of times. So 1950, or do it on your calculator if you're stuck. And then the second bit that we have to, well, we've got 19.5 multiplied by minus x, so it's a positive by a negative, so we've got a negative here when we multiply them, and we've got minus 19.5x. That's what we have on the left-hand side. Over here, we have to do a similar sort of a thing here. We have to multiply 836 by x first, and then second then we have to multiply 836 by minus 20. Okay. Let's take the steps. 836 by x is easy enough. It's 836x. And then this 836 it's by minus 20. This is plus 836 by minus 20, so we're going to end up with a minus here. And we should end up with minus 16720. Okay, now I need to gather up all my x terms onto one side of the equals. and I need to gather up all my just the constant values onto the other side of the equal. So to keep everything positive instead of having negative signs everywhere, I'm going to bring all my x terms onto my right hand side of my equation. So over here I'm going to have 836x, and I want to bring this over to the other side. So what I would need to do is add on 19.5 to this side, because if I have 19.5x minus 19.5x, I'll have 0, so that's what I want on that side. But if I add on 19.5x on this side, I have to add on 19.5x on that side, so plus 19.5x on this side like this. Right, on the other side then, I've got 1950 over here already. This is gone now, and so I have this minus 16,720 on this side, but in order to get rid of it on this side, I would have to add on 16,720, and that would cancel off, but I have to add that on this side as well in order to balance up my equation. So 16,720, like this. And now I just add these two. That gives me 18670 is equal to, and I've got 836 plus 19.5, I've got 855.5x. Now, I've got 855.5x on this side. I want to get rid of this so that I just get x on its own, so I'd have to divide this side by 855.5, but I have to divide that side by 855.5 in order to do that, so I get x is equal to 18670 divided by 855.5. And so I get x is equal to 21.8 degrees Celsius. Right, so my final temperature then, in other words, is 21.8 degrees Celsius. Let's be careful here. If the question asked us what was the change in temperature, of the water, we'll say, the change in temperature would have gone from 20 degrees to 21.8. So the change in temperature would have been 1.8 degrees Celsius, just if it was asked that way. If it wasn't asked that way, it was just asked for what the final temperature is. There it is, it's 21.8. Does this answer make sense? Yes, it makes sense because you'd imagine if you add in something really hot, 100 degrees Celsius, into water that's at 20 degrees, the water would increase in temperature, at least to some extent. Okay, that's that one.